I don't want to, but I do want to cover a bunch of things today, and it's probably way too much and maybe way too ambitious to do all this stuff, but I'd like to at least try to get through some of this stuff and see how it goes. Anyway, so I'm going to do the questions, example one, and I've got to turn my pen back to a color that works, and we'll start again. Okay, so uh, so example problem number one. Yes, sir. You want to see the stuff on the screen? Might help. Okay, example number one. So instead of 1,000, we had 1,250. Okay, so example, and then the first one is the I full load primary, and that would be 52.3. And then the I full load secondary, I got 1,503. And then for the I fault secondary, I got 30,060 approximately. Okay. So if you didn't get those answers, maybe we want to go back through and look at them, but you're grading your own papers is basically what I gave you credit for them if you handed them in. Okay, so if you didn't, if you didn't get it, it's because you didn't hand it in to me, okay? So number two, 75 to 80. Okay, so I get my I full load primary is equal to 96.2. I got my I full load secondary is equal to 222, and my I fault was equal to 4804.9 or thereabouts. Now I used 1.732 instead of 1.73. Okay, I used another digit, so anyway. The next one is 550. Instead of that, I used 650. I full load primary is 850.8. I fault is 15,934. Did anybody get something different than those? Is that it? We're still cooking? Okay, number four. I don't remember what the thing was, but secondary full load is equal to 62.5. I fault, no, I fault was equal to, I fault secondary is equal to 2604, and I primary is equal to 1.08 amps. Number five, I full load primary equal to 4.39. Secondary, as I got is 126. And then I fault, three phase, equal to 5250. Now, are you just going to take these and use these exactly when you get out in the real world? No, you're going to listen to this. You're going to listen to these videos about 3 times before you come up and actually give somebody an answer that's what it's going to be, right? You're going to listen to these videos about 10 times again, right? In order to, right? If somebody asks you, what is that? You're going to listen to these videos about 3 or 4 times and then ask them if that's what they think, right? Because this is scary stuff. And when you're dealing with this kind of thing, you're going to work for a company and you're going to, if they send you out on a job, you're going to come back and you're going to say, well, this is what I've got. Now, what do you think? And in other words, check my figures. Please check my figures the way that you do these things, because I think this guy knows what he's doing, and I think this is pretty straightforward. But now the only question really is, what if you're the person that they hire as the expert in your company, and you're it? Are you just going to trust this, or are you going to call in a consultant? Probably ask a consultant for a little bit of help. And there's some, and you think that's going to cost me an arm and a leg. No, it's not. The people at some of these places like JDRM, you can get those guys for not very much money, and they'll look your figures over and make sure that you're on the right track. Okay? So if you really want to know, you probably could have somebody check your figures over after you've gone through and done this. Or you can have them just come in and do the whole thing, and then you'd be blind and you would never know anything. That's not my recommendation. My recommendation is, if you're the expert in the company, they send you out and you say, this is what I want to do. Then you look at these videos again about 3 times, and then you go out and do your best shot, and then you bring those figures back with all the information you've got, and then you go to a consultant and spend a half a day of their time and have them go over them with you, and then say, is this what you think? And they say yes or no. No, we think this, or we think that, or we da-da-da-da-da. Did you think about, oh, well, how would you do that? Well, then they show you, and then they bill you for that period of time, and that's fair. But basically, they're billable hours. I don't know what they are, $200-300 a billable hour, but it's worth it if you get 4 hours of their time to, maybe $1,000 to check over your figures. It's not the end of the year, or not the end of the day if you don't, not that you pay them, but your company pays them just a little bit to go over your figures. Anyway, all I'm saying is, I wouldn't trust this. I would trust this guy better than I would trust me, okay? But trusting somebody and then actually putting those things down in order to make something actually work are 2 different things. Okay, some things I can do and I know pretty well, but this part of it, I followed primary number 6 is 35.56. I followed secondary is 1020. I got 1020. And I fault secondary is 17,739. As far as I'm concerned, that's what that is. Okay, so that's good. All right, any questions so far? I don't want to present to be the expert in this area, because I'm not. Okay? So number 7, instead of 5,000 and slash 6250, we went 7,000 and 8250. Okay? So I followed primary of 138. I followed secondary is 345.1, and I fault I got is 4881. Okay, number 8. I got the answer of 10,023 amps. That one. Number 9. Here we go from 550 to 650, and this is inrush, and then we've got a 30 horsepower, we have a 75 horsepower, and we have a 300 horsepower. And I got 1.42% dip there. I got 3.78% there, and I got a 14.17% dip there. Number 10, we went from 500, that was his example, and I went to 600. And my number there is 156 kVAR that you have to add. How you add that is up to you. 156. Okay. So that's as far as I went. Any questions anybody has? Any comments anybody has? So that, and then a couple of you did not do the Transformer 101. So you owe me, a couple of you did all four of them. Most of you did all four of them, but a couple of you didn't do the XFMR 101, which is you owe me, a couple of you owe me, and I don't remember who it was, and I don't really, whatever. But that's a grade. It's part of your grade, and I'm counting that as part of your homework. This is going in your homework grade. So again, you did these two exercises. I split it 1 through 5 and 6 through 10, and then those 4 reviews went into your homework assignment. So now you have 6 homeworks that you have done, and then you got your quizzes, which you're doing those on a regular basis, right? Those may not be fun, but daggone it, it sets you up. You'll know more walking out of here about the National Electric Code than most people. Okay, so here again, we're going to go back and we're going to look at grounding. Okay. That's why I set up the, and by the way, the other day we were troubleshooting this, you know why the speakers wouldn't work? The little power that went into this, back of this was sitting in there, but it wasn't in there tight. Usually troubleshooting is something simple, and that's exactly what it was. Anyway, dumb, but I didn't see it. So we're going to go and we're going to look at a grounding and bonding these are short. Come on, Ted.
Tear up your car insurance bill and try this instead. I used to let them raise my car insurance every year until I found this huge loophole that insurance companies don't want you to know about. I was paying over $150 for car insurance.
So we talked about grounding the other day, right? We're gonna nail this down.
Hey Tom, do you run into a lot of questions about the NEC code?
Well, Dan, Article 250, grounding and bonding, that's a big area where there's a lot of confusion. And you'll get a lot of debates, even at the code panels, amongst engineers and installers on all the different terms that we have to use and getting everything the same and everything right. It's a target-rich environment for questions.
Rick, how about for electricians? I mean, is it really pretty straightforward, or do they kind of know what they're doing?
We run into a lot of confusion about grounding and bonding as far as transformers, bonding XO, when to bond, where to bond, with the different starts and stops of service, earth ground, building steel, foundation grounds. There's a lot of confusion based on that.
I mean, I see it with power quality. It's like, if it's 3-wire, 4-wire transfer switches, all this kind of stuff, even coming down the pole, going into the resi room here, where do we ground it, where do we bond it? I mean, at the end of the day, if a power quality person says they don't understand a problem, a lot of times, or if they act like they understand the problem, but they really don't, they might say, oh, it's grounding related, and they kind of just move on. That's a problem for me.
It's very confusing as an electrician to take the theory and apply it into the actual applications. So the more hands-on you can get with it, the better we can all become as installers and engineers, and more problems will get solved ahead of time instead of after the fact.
There's a lot of theory there. Getting your hands on equipment in facilities that provide that ability in an electrically safe, controlled environment, that's the key. That's where the rubber meets the road, actually seeing the fittings, seeing the bonding and all of the meeting the National Electrical Code and practical application of grounding and bonding. It can't be replaced.
I agree.
Why are we talking about this? Why do we worry about grounding and bonding? We're worried about and we want to establish an effective ground fault path, and we also want to think about those touch potentials or step potentials for two different reasons. First, the effective ground fault current path. We're intentionally constructing a low impedance conductive path that's designed to carry the fault current from the point of where the ground fault occurs in the system back to the source. And the reason we do that is we want to make sure that we open the overcurrent protective devices, which could be equipped with ground fault protection of equipment or GFCI protection. We want to make sure that we open those and give enough current for those to detect that fault. Now, you want that impedance to be as low as possible because we want to drive the fault current as high as possible. We have to understand the basic principles of ground fault currents will flow anywhere they can get a chance to. We're not going to guarantee that only the fault currents will flow through the equipment grounding conductor. And that's why we can't make the mistake of thinking that this grounding and this bonding will prevent someone from the electrical hazards of shock. When we talk about those electrical hazards of shock, we want to reduce our touch potentials or our step potentials. We want to keep everything at the same potential and be like that bird on a wire. So we expand this concept. If you think about the concept of touch potentials or step potentials and keeping things at the same potential, you can think about this in regard to substations, where we establish that grounding grid underneath the substation, or around swimming pools, where we're doing equipotential bonding. This will reduce the likelihood of voltage potentials, and we understand that a potential difference between two voltages is what's going to drive current. So if we can reduce or eliminate that potential difference, we can reduce the likelihood of shock, so we can reduce the likelihood of damage to electrical equipment.
With respect to grounding, transformers are often an area of concern and discussion regarding when, where, how, and why to ground the transformer. This is a simple single-phase example of a transformer like a 480 to 120 volt control power transformer. Considering the secondary windings, one of the two legs, typically X2, would be connected to ground. This would allow you to establish a reference to a known reference on the secondary of the transformer when this is required for safety, power quality, or by NEC requirements. X2 is also considered the neutral conductor for typical low voltage applications and would only be grounded at the transformer and at no other point downstream on the circuit fed from the transformer. For this situation, a simple wire connecting X2 to the incoming ground wire coming from the primary of the transformer would suffice for a control power transformer. This ground would also be bonded to the transformer case to ensure that the case and all metal parts remain at a constant potential for reference to the known ground conductor. I've seen many instances where this ground connection was not done to supposedly make it better for power quality reasons, but yet it almost always made it worse without the ground connection, and electrical equipment was damaged. Why do we only connect ground once? Well, if we incorrectly ground the neutral downstream of the first connection, here's the problem. Load current will return on both the neutral and the ground conductor, which is connected to all the metal parts in the system. For that reason, current will divide at the subsequent neutral to ground bond, and load current will flow in the ground. We absolutely don't want current to flow in the ground conductors unless there's a ground fault. Having a single neutral to ground connection ensures that this will be the case. In this next section, we will explain how this applies to larger three-phase transformers.
Are you researching dental implants?
There's a lot of dental offices that'll talk about doing their teeth in the day process.
Let's start with the simple definitions that we find in the National Electrical Code, or the NEC. And we're going to focus on Article 100, where most of the definitions are spelled out for us. Terminology is really important when we're communicating around grounding and bonding. So these definitions are going to be important so we're all speaking the same language. And what we're going to do is we're going to start with the term ground. The National Electrical Code tells us that ground is the earth. I think it's the shortest definition in the National Electrical Code. We define ground as the earth. So anywhere where you use the word ground, you're thinking you're tying to or you're connecting to the earth. Because the earth does not come with terminals, we have to establish a connection to earth, and we do that through what we call the grounding electrode. So a grounding electrode is a conducting object used to make a direct electrical connection to the earth. This is typically your ground rod, very common solution with regard to your grounding electrode. It could be your grounding grid, it could be the U for ground, or inside of a building, it could be the structural steel, the water pipe coming into your home. Those are all grounding electrodes. And you could have multiple grounding electrodes at any one installation. And what the National Electrical Code tells us is that we need to connect all of those grounding electrodes together, and we create what the NEC calls the grounding electrode system. The grounding electrode system is when we pull all of those grounding electrodes together. So every grounding electrode that we have on that site, whether it be the U for ground, the water pipe, or other means that are identified in the National Electrical Code, we have to pull all of those together as a system. And that we call the grounding electrode system. Now let's talk about the grounding electrode conductor. This is the conductor used to connect the system neutral conductor or grounded phase conductor or the equipment to the grounding electrode system. Grounded, when we use the term grounded, this is when we say we are connected to the earth or to some body that extends that earth connection. Ungrounded is just the opposite, right? It's not connected to ground or to a conductive body that extends that ground connection. All right, so now we're going to talk about the grounded conductor. Now, this is the system or circuit conductor that is intentionally connected to the earth at that one point. We usually refer to this as the neutral. And its ugly brother, the ungrounded conductor, a circuit conductor that is not intentionally connected to the earth. So this is usually your phase conductors. Your grounding conductor. I know we're saying a lot of terms here with grounded conductor, ungrounded conductor. Now we're going to talk the grounding conductor. That's a conductor that is used to connect the equipment or the grounded circuit of a wiring system to a grounding electrode or to the grounding electrode system. Now, bonding and jumpers. So we're going to get into an area where we're pulling things together now. We're talking about bonding, and what the National Electrical Code defines bonded as connected to establish electrical continuity and conductivity. This is a very important term as we work throughout the power distribution system. Bonding conductors, or what we call jumpers. These are your reliable conductors to ensure the required electrical conductivity between metal parts required to be electrically connected together. Your service equipment, so when we get into service equipment, this is where your utility is connecting into the power distribution system. And in this equipment is where we're going to define some very important bonding jumpers. One of those is the main bonding jumper. The connection between the grounded circuit conductor and the equipment grounding conductor, or the supply side bonding jumper, or both at the service. So this is your main bonding jumper, that point where we pull both of those conductors or those systems together. Now your supply side bonding jumper, this is the conductor that's installed on the supply side of the service or within the service equipment enclosures, or for a separately derived system that ensures the required electrical conductivity between the metal parts that are all required to be electrically connected.
Stop buying generic Viagra if you're over 60. You qualify for 9 tablets of 100 milligram generic Viagra.
Now we're going to move over to transformers for grounding and bonding inside of transformers. When we move into a transformer, we're talking more like in a separately derived system. This is your electrical source or other than a service having no direct connections to circuit conductors of any other electrical source other than those established by grounding and bonding connections. That's your separately derived source. So let's talk about that transformer. If I have a very common transformer you'll have in a power distribution system is your delta Y grounded transformer. There is an isolation between the primary and the secondary. You're establishing a separately derived system on the secondary of that transformer. And if we look over at a generator, you'll typically see people drive a ground rod next to a generator. And they'll bond the enclosure of that generator with that ground rod. If they connect the neutral to that enclosure inside the generator, they're establishing a separately derived system. Now, why is that important to understand that action will create a separately derived system? Because it will drive what you do in the transfer switch. If you bond that neutral to ground in the generator and you establish a separately derived system, you're going to need to switch the neutral in the transfer switch. And that would mean that you would need a 4-pole transfer switch instead of a 3-pole transfer switch. And if you're bonded in the generator and you're not switching the neutral, you have 2 separate areas where that neutral conductor is being bonded and you could have circulating currents. You could cause GFCIs or ground fault protection of equipment not to work and function correctly. A simple fix, if you didn't buy the right transfer switch, 3-pole transfer switch, and you bonded that neutral in the generator, is to just lift the bond in the generator. Your generator instructions will tell you how to do that. Now, we've established what a separately derived system is. And we know that depending upon, especially in the case of a generator, depending upon how you bond things in the generator and you establish a separately derived system, that will drive the solutions that you purchase and install. A non-separately derived system, good examples of those are your downstream panel boards or that generator that doesn't have an established neutral ground bond in there where you're using the 3-wire or a 3-pole transfer switch. Those are your non-separately derived system. You're keeping things separate. You're keeping your grounded conductor separate from your equipment grounding conductors in all of those locations. All right, so let's talk about the system bonding jumper. This is the connection between the grounded circuit and the supply side bonding jumper. So we have a grounded circuit conductor out there. We have a system ground where we're establishing our ground, and we're going to need to bond those 2 together, and that's what this is all about. Your equipment bonding jumpers, these are your connections between 2 or more portions of the equipment grounding conductors. We have to make sure that we bond everything together, and anytime we put jumpers in between your equipment grounding conductor and any of the steel that needs to be bonded, those are your bonding jumpers.
I've patched the same roofs for years. Same leaks, same problems. That's why I only install stone-coated metal roofing.
Equipment grounding conductor. So we've used that term, let's define it. The equipment grounding conductor is the conductive path that is part of an effective ground fault current path and connects metal parts of the equipment to the system neutral or grounded phase conductor. And that's done back in one location. Think of this as that bare copper conductor that you carry out to all of those loads. Or if you open up any receptacle, you'll see that bare copper conductor that's in the receptacle outlet. That is your equipment grounding conductor. We want that to be a low impedance, and we want that to carry fault current should a fault occur, a ground fault occur in the system. All right, so everything that we've talked about so far has been about grounding and bonding of components and electrical systems. We're establishing that connection at the service or at our separately derived system between the grounded conductor and our equipment bonding and ground and earth. Now we're going to talk about system grounding, and we're going to hit solidly grounded systems versus resistance or impedance grounded systems. Solidly grounded, when we use that type of terminology or that type of a system, we have a solid connection to the earth at some point in the power distribution system. There's no resistor or impedance inserted in that connection point. Ungrounded systems are just that. There's no connection to ground or a conductive body that extends that ground connection. We're insulated from ground. Your impedance or resistive grounded systems. These are systems that are connected to the ground, to the earth, through an impedance. All right, last statement about grounding, objectionable currents. Now, we use this term objectionable currents in Article 250 of the National Electrical Code, but you know, there's no definition in the NEC. And when there's no definition, you know what you do? You make it up. So this is my definition. Current flowing on the effective ground fault current path during a non-faulted condition. And I think to best understand this, let's just talk about an example that you are probably well aware of because it received a lot of attention over at least the last 2 cycles in the National Electrical Code. And these are those motion sensor switches, type switches, that you'll find in either residential homes or commercial buildings, where you walk into a room and it turns the light on. If you think about how we wired residential homes or any types of structures when we came down to a light switch, what did we do? We brought one set of conductors, and that was our hot conductor. And we brought an equipment grounding conductor as well. And we did not bring a neutral. When we had a standard light switch, that was perfectly fine because we're just breaking one conductor. But when you install a product like a motion sensor switch, which needs to have power, so you need a neutral conductor to provide the potential voltage to power up electronics. If I opened up a light switch and I don't have that neutral conductor there, I could get that power by taking hot to ground, the equipment grounding conductor, to power up that unit, and it would work. But it would put current over the equipment grounding conductor. And based upon the definition that we just created and just talked about, that would be current flowing on the equipment grounding conductor that's not because of a faulted condition. That would be what we call objectionable current. And that is not permitted by the National Electrical Code. So changes have occurred over the last few cycles, one, to prohibit the use of those products, and two, to require the pulling of a neutral at those switch locations. So in case you installed a technology that required to be powered up, you're not likely to grab that equipment grounding conductor to get that done. You will properly use the neutral grounded conductor to get that done. So hopefully that helps you understand what we mean by objectionable currents. And remember, all of these terms that we just talked about, it's critical that we use these terms correctly as we communicate to make sure that we all understand each other and we get things right. And hopefully this little review helped you.
This Charmin Ultra Soft Smooth Tear has wavy edges.
It's no ordinary square. Charmin Ultra Soft Smooth Tear has wavy perforations that tear so much better, with more cushiony softness. Enjoy the go with Charmin.
Check this out. I'm going to show you how I afforded this car. Okay, you ready? All right, 100.
For a larger electrical system, we have to consider many other things to properly ground and bond this electrical system. We will give a few examples of components and systems to hopefully clarify any confusion that may arise. Let's talk about two important terms: service entrance and separately derived systems. Simply put, think of service entrance as the electrical equipment fed from the utility source. This may include a transformer, a service disconnect, or other protective devices. There are very specific rules in the National Electrical Code for service entrance equipment and grounding. Think of a separately derived system as a point downstream of the service entrance equipment where electrical isolation creates a new source. Usually, this is a new transformer connection or perhaps a generator. In either case, a new grounding and bonding scheme is required for this separately derived system. Here's an example of a separately derived system with delta Y three-phase transformers. Here is the grounding electrode conductor, and the main bonding jumper. This establishes the grounded conductor that we talked about in the previous section. Let's show you how a residential service and a load center are typically grounded and bonded. A residential system is a solidly grounded system with two hots and a grounded neutral conductor, which is a single wire. This allows the utility to ground the transformer and you to ground your main load center without dividing the current going back to the source because there's only one wire. NEC section 250.20b tells us that all premises wiring systems shall be grounded when the voltage to ground on the ungrounded conductors doesn't exceed 150 volts. So now let's look at a commercial power distribution system. As you get outside the residential world, you have more options based upon the applications. For example, data centers and other systems that demand a higher service continuity may opt to use high resistance grounded systems as opposed to solidly grounded systems. Many commercial and light industrial systems will be solidly grounded. Let's show you how a pad-mounted transformer might be grounded and bonded, and how the indoor switchboard might be grounded and bonded for a solidly grounded commercial power distribution system. Finally, for larger systems using unit substations and switchgear, here's how the grounding and bonding is done for those systems. For larger systems like the pad-mounted transformer or the switchgear, if the utility owns the transformer, we would see the neutral to ground bonding jumper installed inside our switchboard or switchgear, and we would bring the grounding electrode conductor into that service equipment. That is why it is clearly marked as service entrance equipment or suitable for use as service entrance equipment because it has the capability to bond the neutral to conductors inside that equipment. The transformer is a very important piece of a power system puzzle because it establishes the voltage levels and that neutral point on the power distribution system. Depending upon the winding type, the transformer establishes the configuration that you will have to use. For example, the transformer connection may be a typical one like the delta Y, or maybe more unusual like a delta zigzag or a high leg delta. Well-established methods for grounding and bonding these transformers can be found in our consulting application guide.
Discover your new Mazda right now at Yark Mazda. Come lease a 2025 Mazda CX-50.
Now, everything that we have just discussed around power system grounding is separate from the bonding discussion that we had because regardless of the grounding method for the power distribution system, the equipment grounding doesn't change and bonding is still critical and required. The difference is that the grounded conductor and the grounding conductor must be insulated from each other outside of one point in the power distribution system where they're bonded. Any subpanel in a power system must not have a connection from the grounded conductor, which is typically the neutral, to ground. Remember too, this is only relevant if you have a grounded conductor because with a delta high resistance system or an ungrounded system, you're not going to have that grounded conductor.
Power quality considerations are important as you consider when, where, how, and why to ground your power system. The key is to focus on things that can be controlled and solved. The main power quality concerns that are usually the focus of grounding studies include lack of proper grounding. Beyond the safety concerns, equipment can and will fail with improper or inadequate grounding. In addition, surge protection will be ineffective if it doesn't have a proper path for high-frequency currents. Improper wire size or type and painted surfaces. For example, 60 Hz currents will generally penetrate painted surfaces during fault conditions, but oftentimes higher frequency currents may or may not be adequate to provide low impedance path for stray or unwanted currents from electronic components or induced currents from PWM inverters. In most cases, highly stranded and braided cable or bus bar with the shortest possible length is the most appropriate grounding method for high frequency currents, as it provides significant surface area for the skin effect phenomena of high frequency current. Circulating currents, ground loops, isolated grounds, and single point grounding. This can be a slippery slope, and oftentimes it's problematic to force a system to have a single point grounding for quote-unquote sensitive equipment. I've seen plenty of situations where ground loops from AV equipment has caused electrical noise and must be eliminated, but there are well-proven methods for dealing with this situation. It's often thought that dirty power grounds should be kept separate from the sensitive equipment grounds, but this is not only dangerous, but risky from a power quality standpoint and potentially damaging to equipment, aside from the fact that it's an NEC violation. We gave an example of a situation where isolated grounds were a problem with a lightning strike and improper grounding in our power quality solutions video. Isolated grounds like you would find on a hospital plug are a different story and can certainly help from a PQ standpoint, but should be installed with care and as intended. The bottom line is that PQ problems related to grounding can be handled, but they should be dealt with like any other power quality problem. Identify the symptom, find the source of the problem, and determine the right solution. But if the problem seems unsolvable, don't just blame it on grounding.
Stop buying generic Viagra if you haven't tried this new 87-cent generic Viagra from Friday.
For systems with transfer switches, if separately derived systems are to be joined via a transfer scheme, only one neutral to ground connection must exist. Let me show you how you can accomplish this with a typical power system. So let's just take a quick look at an example system where you would have a transfer switch, and obviously you have your utility and your service panel. Off of your service panel, you'll have your grounding electrode. Your grounding electrode conductor will come up to your neutral bar, and then you'll have a bonding strap between your neutral bar and your equipment grounding bar. You'll have a feeder come off of your panel board and feed the transfer switch. On the other side of that transfer switch, we have a generator. The generator will be connected directly to the transfer switch, obviously through some overcurrent protective devices, and then your transfer switch is going to supply loads. So this is a basic layout of a transfer switch with a generator in a system. Now, sometimes people will drive a ground rod and bond the generator hull or the structure to that ground rod, and that ground rod is supplemental. So it's not required by the National Electrical Code. It is a supplemental type of grounding. A purposeful connection between the neutral, that grounded conductor, and that ground rod system, the grounding system over there on that generator, may occur in the field, either on purpose or by mistake. The important thing to understand is when you make that connection, you've established a separately derived system. So when I have a neutral conductor bonded and grounded in two separately derived systems, remember I have it grounded and bonded in my service panel, I have it grounded and bonded in my generator, I need to make sure that I only have one place where that occurs, and to get that done, I need to switch the neutral in the transfer switch. So that means I would need to have, say for example, a 4-pole transfer switch. If I do that, I put a 4-pole transfer switch in, I switch the neutral, everything is fine. A separately derived system implies that you would have a grounding electrode system and you would bond the neutral, the grounded conductor, in the generator with that system. If you have a separately derived system, the implication is that the transfer switch must switch the neutral with a 4-pole transfer switch. But what if I accidentally bonded the neutral to the ground in the generator and I only have a 3-pole transfer switch? How do I fix it? Do I have to buy a 4-pole transfer switch? Sure, you could. Or you could simply unbond the neutral in the generator. But you must be extremely careful on how you operate a system like this, because the return current for the generator neutral will flow back through the other separately derived system or transformer. This is especially important for the electrical workers who will be servicing the equipment.
What do you think? You scared? Now you're going to switch to economics or something? Okay, so in my case, I was always a controls engineer, and there was always a power engineer that worried about this stuff, and all I had to do was hit him with a ground wire. I was good to go. I'd say, "Where's my ground?" There it is. Hook it up. I was good to go. I didn't worry about this stuff. But if you walk into a situation where you're both the electrical controls person and the the only person on site that does any power work, you're gonna have to know this stuff. And maybe you want to be a power engineer and that's all you do. I'm not trying to convince you that you should do controls, but I'm saying that if you do work in the power industry at all, you have to know this. This is not an option. What this was today is not optional. You have to do this stuff. You have to know how to do this stuff. It's not like you can get away with it unless you have a power engineer that's working side by side with you, and in all that case you do this and you're good to go, like I've always been. Okay, now I'm not done. You may be done. The other day I cheated you too short. Maybe I'll cheat you today too long. I don't know. But I did do another subject, and this is having to do with the idea of harmonics. So I put this in your on your thing. It's a totally different topic, but it's not. And I just kind of wondered Do you know why hummingbirds hum? Obviously, because they don't know the words. But what is harmonics? What is harmonics? Okay. Well, harmonics is basically above the base frequency. It's a frequency that goes above that frequency. So basically, you have your 60 hertz or whatever. Okay, you have this going, right? You've got that, and everybody buys that, right? We've taught you to believe that that's it. Okay, what would be a harmonic of that? Well, this would be your base frequency. An harmonic above this would be maybe 3 times that rate, or 5 times that rate, or 7 times that rate, or 9 times that rate. But they would hit at these points that they would actually hit. Okay, so a 3 times it would be, I can't probably draw it, but it would be something that looked like it would go 3 times as fast. It would go 1, 2, 3. So this would be, that would be a harmonic. That'd be a third harmonic. Okay. Fifth harmonic would be 5 of those, and seventh harmonic would be whatever. Now, what does this do? Okay, as you go higher in frequency, what happens? Okay, 1 over j 2 pi f c and j 2 pi f l. Okay, so which one of these, as you go up in frequency, gets smaller? As you go up in frequency, this goes, the x sub c goes down, okay? The x sub, as frequency goes higher, x sub l goes higher. So basically, inductance isn't a problem, but if you have capacitance in your system, you go low and you get lower in the x. So as you go, as x sub c goes down, what happens to current? Excuse me. What happens to current? I goes up. Okay, so if you see hot spots in your equipment, in other words, if you take a UV picture of your equipment and you actually look and see what is there, if there's a, no, it's infrared, excuse me. If you take an infrared camera and you look at where the infrared is, if you look at it and you can see certain areas that are really warm or hot or really, really, really hot, it's probably because of this. Could be something else, but it's probably because of this. Okay? So let's go back and look and see where those came from and why it's important that you might noticing them about harmonics. Okay. Now the good news is that this is improved, but this is notice the date, 1999. Effects of harmonics on power systems. Okay, so this guy is warning us about power systems at harmonics, okay? So I did a chat GPT of this, and then I dumped all this thing out. Now this was featured in ECNM. Okay, so this was a big long article on ECNM in 1999. So now I go back and I look at my buddy. Okay. I read through this article, and that's on your web. That's on your web. So I asked my buddy at ChatGPT, are harmonics today less than in the past due to improved inverter design? Okay. And the answer is yes. Older inverters use thyristors or simple IGBTs with low switching frequencies, and these produce strong low-order harmonics, 5th, 7th, 11th, etc. They were hard to filter. Modern inverters use fast IGBTs or SiC, calcium nitrogen transistors, switching in the tens of tends to hundreds of kilohertz, okay? This pushes the distortion to much higher frequencies, which are easier to filter and don't propagate as far in power systems. Okay, so now early designs were based on, for inverters, were based on square wave or 6-step switching. Today, sinusoidal plus modulated, and we're going to talk about this, we're going to actually see this, give you a much lower harmonic availability. Okay, so anyway, so if you have an old facility and you walk into it and they've got motors there that are running very, 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 very hot. By the way, what is TDH? Total harmonic distortion, TDH, THD, total THD, total harmonic distortion levels. Okay, so if you have old equipment, you have more THD than with newer equipment. Okay, THD. Okay. So be thankful for the improvements in the designs of inverters, other things as well. But THD is, it says, usually staying under 5% is okay, sometimes as low as 2%, and that's better. That's better than what used to be. THD, total harmonic distortion. Now let's go back and let's listen to our buddies again at Eaton about harmonics. Again, it's why hummingbirds hum. Ready? Caraval.
One of the questions we get a lot of is, what does an AC line reactor or a DC choke do for my drive system and reducing harmonics?
We're not going to go through all these. We're just going to get to the first one. There's a bunch.
So this is a DC choke, and this is an AC line reactor that you might find in front of a 30 horsepower drive. This would be in front of the drive. The DC choke, there would actually be a pair of them or two of them inside the drive. I'm going to show you real quick an example or an analogy of what a choke does. When we say the word choke, we constrict the flow of harmonic currents or high frequencies. If I took a hose and I had water flowing through this hose and I constricted the flow or pinched this hose, I wouldn't be able to get as much water through it. And it would constrict the flow of the water through the hose. So in a similar way, if we have conductors in the power system and we have line reactors or DC chokes constricting the flow through the power system from the harmonics, which are high frequencies, we're not going to allow as much high frequencies to come out of the drives and flow back into the power system. Now, if we take a look at this graphic shows about 80% distortion for a drive that has no line reactor in front of it. In fact, every drive has about 0.5% built into it inherently in the conductors. But if we purposely put a 3% reactor or choke, we get a reduction of about half. We get down to about 40% distortion. Now, if I had a transformer in front of my drive, what would that do? Well, the transformer impedance, a typical impedance on a transformer might be 5 or 6% impedance. That impedance acts like a line reactor does in front of the drive. So it constricts the flow of the harmonic current. The question is, if I put more impedance in, do I, create a significant amount of reduction? And it's kind of diminishing returns. So if you look at this graph, we go from, 0.5% to 3% to 5%. You can kind of see diminishing returns. If I go as high as 10%, for example, I wouldn't get, double the amount of reduction as I get with 5%. So it's, again, diminishing returns. So as we look at that, how much does my transformer come into play if I have a transformer in front of my drive? Let me show you an example of putting a transformer in front of a drive and what we would do to reduce the harmonic currents. So if I have a transformer, let's say it's a 30 kVA transformer, and I have a drive, and let's say that drive is 30 horsepower. Well, horsepower is about equivalent to kVA, so if I have 30 horsepower, I have about 30 kVA. Now, if this impedance, or Z, is 5%, then I effectively have about a 5% line reactor, because most of that impedance is inductance. But what happens is, what if this drive is not 30 horsepower? What if I have a 15 horsepower drive here? Well, the equivalent impedance then would be 15 kVA, because we said kVA is equivalent to horsepower, over 30 kVA, times the 5%. So I'd effectively get about 2.5% impedance or reactance in front of that drive. And again, so the reduction is going to be, instead of being something like this, I may get something like this, which is going to have more harmonic current involved with the system. So again, as we look at line reactors, DC chokes in front of a drive, it's the most cost-effective benefit to put inside a drive or in front of the drive, because it does the most for the least amount of money. It doesn't get you below the levels maybe of IEEE 519 off the shelf, but it's a significant reduction. And all of our DG1 drives, for example, have 5% DC chokes built into them. So I would highly suggest looking at buying drives that have that impedance built into them off the shelf.
Okay. So now that you've kind of just got a little bit of an idea, now why did they put the choke in front of the drive? Because the noise, the harmonics, is in the drive itself, and they want it to not come out of the drive and go back onto the line. So basically you're protecting the harmonics emanate from the drive, the thing that controls the motor, and that leaks back, and so they want to keep it off of the main. They want to keep the AC outside of that as clean as possible. That's why they put the choke in. Anyway, so we're going to get into inverters and all that sort of thing a little bit later, but I want you to understand that harmonics can have an effect. I honestly never thought that I would be working in any area that had anything having to do with harmonics, but that little, if you're doing the 4450 class, the little pump that we use that has it's the bilge pump. The bilge pump has a capacitor in it, okay? The tank on tank, the bilge pump. So here's the tank on tank. And at the bottom there's a pump. And it has a capacitor in it. And we feed it with a signal that here's your 0 volts, and we go 24 volts on off, which is a classic way of doing that. Now, if you want to go full on, this would be maybe 70%. This would be 70%. Okay? If you want to go full on, you would just turn it on and let it rip. If you want to go half on or a quarter on, you would do. So this has harmonics in it. Okay? It has your DC waveform, but it has harmonics. Any periodic waveform has, other than a pure sine wave, has harmonics in it. So this has harmonics that basically go high in frequency, and because this has got a capacitor, high frequency, lower the impedance, and that little capacitor sits there and gets really, 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 really hot. So you would never do this. See, once you put a big capacitor on that and smooth this out, and that probably would have worked. We've been afraid to, because we didn't know how big a capacitor to put on it. So if you want to, we would smooth this out by putting in a capacitor that basically that would do this, would do that. We've been afraid to, was how big the capacitor has to be to put it on, but we've not done that. But that would be a fix. But in essence, what happened was, because these harmonics and this signal heat up that little capacitor there, it sits there and gets so hot it could actually burn up, except for the fact that it's underwater and the water cools it. So you think, what did he just say? Is that a poor design? Yes, but we lucked out because the water keeps it cool enough that it doesn't fry. But if you run it for a while with no water, you could sit there, you could fry an egg on that little pump. So anyway, again, you don't always think about these things having to do with real world, but there it is, and it comes up and bites you every once in a while. When they were talking about higher frequencies in a wire run, if you look at this cross-sectional area of that wire, they call it the skin effect. The higher frequency currents run on the outside of the wire, not on the inside. And you say, how do you know that? Well, good old Maxwell's equations prove that for you. So if you really want to know why high frequency, all the current travels on the skin at a higher frequency. And there is a derating in the National Electric Code of wire based on the frequency of the signal. And when you get to really high frequency waveforms, you can use a copper pipe as opposed to a wire to carry your current. A fact. So anyway, any questions anybody's got? Score scare you. What's going to happen next, right? Did anybody have any questions? Now, the other thing I wanted to tell you was that the one thing that if you look at the one lines, okay, in the example, the one-line examples, and then what I'm expecting you to do, there is one thing I want you to do in addition, and that is to size the wire and the conduit. The examples do not show that. But because we've given you all the details, you can size the wire and the conduit. So as each of those come down, as you go to a device, you do a little thing like this, and it says 3, number 12, AWG, and 1, ground, whatever, number 14 or whatever. But you need to size those as well in a 3/4 inch conduit. So you need to put those tags on as you're doing this. They're not hard, but they're doable. Okay. Thanks. Take care. Have a good day. Should I bring the speakers or not? Is it okay with